first in the part mo- first in the part module, let's go to create part manager, and then you have to create the three parts, which is descaler, roller, and stop. Create with the part name, 2D planar, deformable, and a shell. Approximate size can be anything, but I've taken 200. 2D planar because we are trying to problem a plane strain condition, and then after creating the three as with the required dimensions. And this is a roller, and then this is the stock of initial with 500, and we can see the shape is given in R2, help in biting position, and then we have a roller of 450 mm outer dia and thickness of 35 mm here. So the thickness can be found by using the diffusion length formula, which is 4 alpha t under root, wherein t is the diffusion interaction time for the length that comes out of the roller. And to have a protection, we consider the thickness of the roller to be 5 times of the diffusion length. Yes. So then the part model is done, and then we go to the property manager. Here in property material manager, first we need to create the material, that is roll material and stock material respectively. Uh, so I'll show the already existing one, which is the roll material, conductivity. Then we go for density. Here I have taken a mass scaling of 100, so I have increased the mass density by 100 and reduced the specific heat by 100, so that uh, the simulation can be done in a faster way without affecting the end results. And then we have elastic properties, which is Young's modulus and Poisson's ratio, and conductivity is here. Yes, conductivity is from the thermal properties. Then from mechanical we take elasticity, elastic, and plastic, and from general we take density and specific heat from thermal. Yes. So coming to stock material, we go by density, then conductivity, density, elastic modulus, which is a function of temperature. So we get the values accordingly. Then expansion coefficient, inelastic heat fraction, which is zero point 0.9. Plastic data uh, for as a function of strain rate dependent and temperature dependent data is given here as follows. And then the specific heat by the same method of scale factor of 100. Now after giving the material data, we go creating the sections, which is a roll section, and then a stock section. Over here we select mean, homogeneous, and solid, and give the section name accordingly. Now once the sections are created, we assign the sections to the to the parts that we have created. Here a roll here the roller is given a roll section. For example, create, select the part, done, and then we select the material that the section we have created. Since I've already done, I'm not going to select it. And then sorry, and then we go for the roller descaler. Descaler is also having the same properties as that of a stock. And then so we have created section for assigned the descaler to have a stock section. The stock is to have a stock section again. Once this is done, we are complete with the property module, and then we go for assembly. Since this is two stage module, we have two descalers to see. Okay, this is the first descaler, and then we have a roller, and then a descaler over here, and then again a roller over here. Okay. Uh, so based on the exact geometry, we have to go to assembly over here. For the first roller, the stock is at a distance of 13.75 meters, and the scale is at uh, 5 meters, 5 meters approximately. And uh, as the descaler, as the stock moves, it touches the descaler. Thereby, there's having some thermal exchange over there because the descaler removes the heat out of it, and then further passes the descaler to the roller, where the deformation takes place from initial since we have done it on a single plane set, we can make it as we can image it symmetric over here. So the initial thickness was about 57 mm. So we have a problem rate for 28.5 mm as a single plane thing. So 28.5 mm is reduced to a thickness of 11 mm at the first stage, and then the second stage considered the thickness to be reduced to about 8 mm, that is 16 mm in total. And the second roller is at a distance of 5,500 mm from the first roller, and the D-scale is between both of them. After assembling both, after completing the assembly according to the uh, geometry that we have set, we then go to the step module, wherein we have to create four steps over here. The initial is initial one is by default, and then we have step one, which is fluctuated. Since the problem is a dynamic temperature displacement explicit, yeah, dynamic temperature displacement explicit problem. Uh, so the first step, we have calculated that since it is assumed that the stock moves with an initial velocity of 1 meter per second, so it covers the distance about from the initial distance to the first roller about 13.74 seconds, and in LGM is to be on because it's a non-linear geometric deformations are to be happening. And since it is a dynamic temperature displacement and explicit problem, we do not alter any other incrementation or masking properties over here. Then similarly in step 2, we need to find the uh, interaction time, that which is about 1.6 seconds, and then from roller 2 to roller 3, roller 1 to roller 3, it is a distance of 5,000 meters. So it is and 5,000 meters, and since the stock moves with an velocity of about velocity after coming out of the roller will be equal to that of the roller velocity, that is 820 millimeter per second. So with respect to that, the time comes out to be 5.1 seconds respectively, and then in step 4 it is the same. We need to find interaction time between the stock and the roller uh, by volume constancy principle over there. So we get a time for about 2 seconds for that. This is our step is module, and then we go to the interaction. Here first we need to give some constraints, which are descaler descaler 1 and 2 both are to be rigid, and then we have the rollers also to be rigid with respect to the reference point that we have created. Here we go for the content continue. First we need to select the body element over here. In this case you can select either the descaler entire body or the roller entire body, and then we go to the reference point of it, so that the the rigid conditions can be enabled over there. This is how the constraints are given over here. And coming to the interaction property first. Here we need to give two interaction properties. One is descaler and stock, the other one is roller and stock. Wherein when we try to create it, we go by contact, continue. And then in mechanical, we go by, so let's see the existing one. If we check the roller stock interaction property, in mechanical, we take a tangential behavior and normal behavior, wherein in tangential, we give a penalty of 0.25, which is a friction coefficient, and then in normal behavior, we take a hard contact default, allow separation after contact. This is so that there is no penetration of the object into one another. then from thermal we take the thermal conductance and heat generation. Thermal conductance is given as a function of clearance. Uh, if there is no clearance, then the conductive conductance is about 25, 25, and then we have 12.5 for 2 mm clearance and 0 for 4 mm clearance. Similarly, we have the heat generation, which is taken as default in both the cases. That is, how much amount of heat is moved carried out into the roller or into the stock, respectively. This is for the roller stock interaction, and then we have a descaler interaction where only the thermal conductance is given accordingly with respect to the clearance and the conductance. Okay. Uh, Here in our problem, we are modeling the problem as we are modeling the problem in the units of newtons, millimeters, seconds, respectively. Then we come to the interaction property manager, wherein we can see here a pretty good numbers of it. And first, we give us we give the roller stock interaction pair, wherein mm, the first surface, which is the master surface, is the outer surface of the roller, if we can see here, and then we have the master surface of the roller, and then the slave surface is to be the outer surface of the stock, which is going to interact with that of the roller. And next, then we come to using the penalty contact method because kinetic is not working in this sense, and then we have to assign the interaction property, which is a roller stock interaction property in this case, and then the property gets created and propagated respectively for the initial step, and then we have to give the interaction between the stock and descaler from the initial step, wherein the stock bottom part is uh, selected to be the master surface because that is only the contact that comes with that of the stock, and then we have the slave surface, which is same in this case too, and a penalty contact method, and accordingly the interaction property is given over here. Then we have respectively stock radiation, which is created in step 1, and stock convection, which is created in step 1. Then also we have the solar convection and solar radiation also created in step 1 and step 1 respectively. Let's see how the stock radiation is given. So first we select the entire outer surface of the stock, and then we give the values of emissivity and ambient temperature respectively. Similarly, we do it the same for stock convection, the outer surface of the stock, and then film coefficient, which is H value, that is uh, convection coefficient in terms of the units that we are following, and then the sink temperature is the ambient temperature. Similarly, for the roller convection, roller radiation is also given, where the outer surface of the roller are to be selected. And then we have okay. Then we have other two properties also to be given, which are uh, we have the second descaler and the second roller over here. So respectively, we need to give the properties for them too, wherein the stock and descaler second contact. It's the bottom surface of the scalar, and then this is outer surface of this uh, outer surface of the stock to be the slave, and a penalty contact, and similar the interaction property is given over here. And then we have the roller stock interaction, which is which is similar to that of the first roller, but all these are done in step 3 step 3 as seen over here. Yes. This is how the interaction properties are given in the interaction property model. Then we go to the load model, wherein the first we define the First, we just redefine uh, first we redefine the term. Give some initial roller temperatures. Initial roller temperature in one of the cases is given as se- 70, and then we have a descale initial temperature which is 40. Second roller initial temperature, and also we have this. This is the first one is about velocity to the stock, which is v in v1 direction 1000 mm per second. Stock initial temperature is to set as 1100 degrees Celsius. Yes. Initial temperature for initial temperature. Okay, descaler is also given. We need to give an initial temperature for the first descaler as well. We select the entire body for it. Which is 14 RKS. Yes. So now the predefined models are completed. Now we have to give a lot of boundary conditions which are yes. First we start defining the stock velocity boundary condition. Now we start encasting the descaler. So first selecting the step as initial and symmetric encaster about the reference point RP. Mm. Similarly, uh, similarly for the descaler 1 and descaler 2, both we have to encaster it. Mm. And then we have the stock symmetric boundary condition that is to be given, where the bottom part is selected in the step 1, and we are restricting its motion in due to direction. That is a symmetric property. Descaler encastered, then descaler initial temperature is given over here, which is 40 degrees Celsius. So if we give over here, it's not required to give it in the predefined fields. And then encaster over here, roller angular motion. Okay. We need to ensure that the roller translation 1 and 2 both are locked. That is U1 and U2 from the initial state itself of the roller are locked. This is how the rigid conditions are given to the roller and these scalar respectively. And then the roller angular velocity is about 450 mm per second, and its radius of 820 mm per second, and its radius of 450. So the angular velocity turns out to be of 1.82 radians per second. in V3. This is similar for the second roller too. So and but it's given in the step 3 only because there is no point of rotating it from the step 1. And then the stock velocity from step 1 for step 1 is given around 1000 millimeters per second, and step 2 where it interacts with that of the roller, the velocity is deactivated because the roller with the velocity of the roller, the stock starts moving, and then after the stock comes out of the roller one, it has to be given a velocity of equal to that of the roller, so it moves towards the second roller, and then it's again deactivated so that the roller does the part. This is how the interaction module is given. Sorry, boundary conditions are given to it in the load module after the predefined thing. Then we go to the mesh. We need to mesh each part respectively. First, we go to the stock part. Then in controls, we need to select the quad structured part, and then in element type, after selecting the entire region, we go for coupled thermal displacement, explicit and geometric order of linear, so that we get an element type of CPE4RT, which is a reduced integration in at the end. In explicit, mostly the reduced integration is by default, and then we go for seeding by edges and make sure that the maximum number of elements are taken on the surface respectively. And then finally we mesh the part by going to part, select it, and then yes, this is how the mesh gets generated. Similarly for the roller is also and the scalar, the same mesh has been taken, but in case of roller we go for mesh controls, we go by sweep because it is a circular surface. And this is how mesh is done. Then we go for job. That is where the job has to be done. In this case, let's create one for name check. And then in for repetition, I go by double analysis packager and full. This is to avoid any round of errors that are to be faced over here, so that we can get the proper results. And then we submit it so that the analysis start to run. Since I've already completed the Since I have already completed the analysis, let's go to the results that we get. Visualization. In visualization, this is how it looks. Uh, I'll show. Let's see the module over here. See, this is how. If you can see, there is the movement in the stock and this thing. I'll show it in the closer manner. Okay. See, you can see that the stock moves. Let's see, I have a temperature variation. This here. Okay. Let's go over frame by frame. When the stock and descaler interact, we can see a small difference in the temperature because there's a small amount of temperature has been removed from the stock by the descaler. And then when we go by the other, we go to the there gives me temperature change because roller takes the temperature over here and the deformation takes place. And then further in the second stage, again at the descaler there is a temperature variation. Yes. And then we have final stage wherein the roller takes place. Roller 2 deforms the part accordingly. Now for results, we go into tools, XY data, manager. These are already present, so I'll delete it. Yes. To create it, field output part, select a unique nodal. Let's see for reaction force, and then reaction moment. We'll keep the nodal temperature for the later part. Go to elements. You need to select the 2 points where you are interested. In our case, we are, in our case, we are interested at the reference point of two rollers, so that we can take the we can get the values accordingly. Just waiting for the results. Yes, here are the results for the same. For roller 1 and roller 2, if we try to plot, this is for RF1. We are in interest of RF2. Sorry for that. And then let's go and plot it again. Yeah. Yeah. These are what we are interested in. So you can see at 100 degrees Celsius of temperature, we have initial temperature. Solar one is having a force of around Solar operating force of around 26 to 27 kilonewton per mm of width, and roller 2 is having about 17 to 18 kilonewton per millimeter of width. Similarly, we try to find the nodal temperatures, because we are removing, because we need to have a different selection for that. Um, so temperature is on the stock. Let's say 2 points over here. First point and second. That is how we take the temperatures on the stock. One is on top surface, the other one is on the middle plane. By logic, the top surface is more on interaction with the outer surfaces, so there is a high temperature loss at the top surface when compared to the middle surface. Middle surface, because it is at a very high temperature, the internal heat that is having already is present already. Uh, it will be at the higher side of temperature for most of the operations. Okay, we did not get the values for that. We need this from. Yes. Try it again. Yes, we got it. Here N40. Yes, this is it. So this is the graph that we are looking at, wherein the top, the red line, which is N40, is of the middle surface, and N144 is of the top surface, wherein it interacts with most of the mo- uh, it interacts with most of the elements which is on the outer surface. So more and more fluctuations in the temperature is seen over here when compared to that of the middle surface. These are the results that we can take from the ABAQUS simulation over here, and yes, that is how I have simulated for the rest of the other temperatures, where I'll be changing the values of predefined temperature at interaction module, sorry, load module, going to predefined manager. Here I have a stock initial temperature. I can change it over here to 1100, 1150, 1000, and 1050 accordingly, and simulate the for same. Uh, yes, thank you.